Hey everyone, and welcome to part 3 of topic 5 in our database class. In this video, I'm going to discuss denormalization. And as you may imagine, just based on the name, denormalization is the opposite of the normalization process. That is, we are going to take a database that is fully normalized, and we are going to intentionally and deliberately and very precisely make some small changes to the database that will make at least parts of it no longer fully normalized. And we do that to achieve some kind of goal. And it's typically going to be some sort of performance related goal. Okay? So when we have a fully normalized solution, our design is generally immune to modification anomalies. However, it is more complex because we've broken a big table apart into two or more smaller tables. This table that you see illustrated here, this database design, it's just one table, no relationships. That is less complex. That is simpler than this design here, which contains three tables and two relationships. Right? So we've got customer table, zip code table, accountant table, and then of course these would be related for here, some sort of one to many, some sort of one to many, right? So this is obviously a more complex design than the simple one that we saw in the previous slide. And that is the result of the normalization process. You have more tables, you have more relationships, therefore your design is structurally more complicated. And it is that increased complexity that occasionally creates problems for us. And again, typically those problems manifest themselves in the form of some kind of performance issue. So, as with most things, once we reach a certain level in the database world, there are trade-offs to be considered. When we fully normalize a database design, we are giving up simplicity in exchange for not having to worry about modification problems. I should say we were giving up simplicity and speed in exchange for not having to worry about modification problems. So as our database design increases in structural complexity, things become slower because we have to do things like joins. If you remember when we studied the structured query language, we learned all about joining tables together. And you can imagine if you just think of yourself as a human being and you're joining two tables together, it takes work to do so. So if I have this three table design and I want to do something like just print a report, give me a list of my customers, their addresses, and their names of their accountant. Well, to achieve that, I would have to look in all three of these tables and link all of these records together based on these matching values of primary keys and foreign keys. And so that takes much more work to achieve that result, in this case, wanting to just generate a simple report, than if I had a simple design like this. Right? Imagine how much simpler it is to generate that same report if I have all of these columns just stored in one table. And if I want my report to contain the name and address and the name of their accountant, well, it's very easy, right? There's no joins involved. All I have to do is just look through this table and pull out the values of the columns that I need. So customer's name, customer's address, and the name of their accountant. Right? I just get it all from one place. Just look in one single table. So it's much faster. It's much simpler. There are no joins involved. They don't have to worry about relationships or looking for matching values of primary keys and foreign keys. So what we have then is a trade-off. Right? It's a trade-off. We are increasing intentionally with normalization. We are increasing the structural complexity of the database in order to protect the quality and the integrity of the data in that database by preventing these modification anomalies from occurring. However, when we do that, that increased complexity can slow down query speed. Okay. Because we'll have to do joins and the database will have to take the time to match records and different tables together based on these matching pairs of primary key, foreign key values. So it has to do all this extra work in order to answer the query, and that slows things down. So it's a trade-off, right? And what we find is, particularly in an era of big data, sometimes that additional complexity that has been introduced slows queries down to a point where the overall performance is unsatisfactory. And one of the tools that we have in our toolbox for resolving that, for increasing the performance to a point where it meets our needs or preferences, is denormalization. So there are then plenty of situations in which denormalized relations are preferred. And again, the primary motivation here, the most common reason for doing this is performance related. We're trying to improve the speed of our queries. Now, I want to, before proceeding, I want to say this here, and I've said it before, and I'll say it again. When we are doing denormalization, people that are relatively new to this fall into the trap of making big changes to the structure of the database. And that is an undesirable thing to do. What we want to do is change the structure of the database in the smallest, least significant way possible in order to achieve our goal for doing denormalization in the first place. So often what I see is people will go and they'll turn like they feel that the only approach to denormalization is to merge tables together. Since when we do normalization, we're splitting tables apart. I guess it makes sense that people would think that the only approach to denormalization is to merge tables together. So I'll give people like 6 or 8 tables and I'll get like a 2-table solution back. And it's just too drastic of a change. And we need to remember that these databases do not live in isolation. They're part of a broader information system. So if we make major changes to the structure of an existing database through the denormalization process, we may have to make major changes to all of the software that relies on that database. Right? So you don't want to just go in there with a big machete and start hacking things apart, because in so doing, you will need to also go into the company's website and its mobile apps and its desktop apps, and all these various things that can rely on that database would also need to be changed with that approach. So the general philosophy here is, yes, we are going to alter the structure of the database. However, we want to do so very carefully, very deliberately, very surgically, right? That we want to make very precise cuts and changes rather than big changes. Now, with that in mind, that sort of general philosophy toward denormalization in mind, let's take a look at some of the strategies that we have to denormalize and otherwise normalize database design. So, since with normalization, our one tool for normalization is to split tables apart, it makes sense then that one of our tools for denormalization is to merge tables together. And this is okay under certain circumstances, but we should not look upon this as the only strategy that's available to us. Indeed, this is generally less desirable than some of our other strategies. Nevertheless, there are times and places where this is perfectly appropriate and acceptable, and indeed is the best way of doing the denormalization task. However, we should always consider our other 2 options before merging tables together, because that's a big change to the database, right? By merging 2 tables together, you are entirely getting rid of 1 table. Right? And the relationships between them. And you have to move all the data and all the software that relies on them, all the SQL statements that are built into that software, all of that would need to be changed. Okay? So, although that is a viable strategy and it has its place, it's certainly not the only tool available. And indeed, we should take a look at these other 2 and see if we could make them work before trying to merge tables together. So, our second approach, as I've highlighted here, is that we can add a new attribute to an existing table that will allow us to avoid the necessity of doing a join. Okay. So typically the performance bottleneck, that is the cause of the degradation in query performance, is the necessity of performing a join. I have to join multiple tables together in order to answer the query. So if I can avoid that join, or put differently, if the database is able to answer the question by looking in just one place, by looking in just one table, then it naturally will be much, much faster than if the database has to look in multiple places and do a join in order to answer whatever question we're asking of it. So our second strategy then is we can add an additional attribute to a table that will allow us to avoid a join operation. One thing that I will note when we do this is that we are adding redundant data to the database. So if I say, for example, I take a copy of one attribute from a table and I store it in another table so that I don't have to join them together, that's fine, but I need to recognize that I now have an additional copy of that first attribute. And that exposes me to risk, right? The risk of these modification anomalies, because in that case, we're storing the same information in more than one place in the database. So suddenly I'm exposed to risks of anomalies that creep in due to inserts, updates, or deletes. So I need to keep that in mind. Right. More broadly, whenever we do denormalization, we are going to have redundant data in our database. And we'll have multiple copies of the data. So naturally, that means that we're going to see an increase in disk storage because we're storing copies of data that otherwise we wouldn't have to store. But again, it's a trade-off, right? We're doing all this for a reason. And that reason typically is to increase performance. All right. So thus far then, our two strategies are merging two or more tables together in order to improve performance. Second, we can add these additional attributes to a table. We just add another attribute, for example, and I'll show you some examples of this shortly. But it allows us to avoid a join operation. Okay, so that's our second strategy. And our third strategy is somewhat similar to the second, but in this case, what we're doing is we are adding an additional attribute to a table that stores the result of a common mathematical task. And this allows us to avoid the necessity of repeatedly performing that mathematical task at runtime. So, for example, maybe we want to store the, I don't know, say our total sales for our store, for each of our stores for every day. Right? So we just store that sum rather than computing the sum at runtime when the query is submitted. So I could just create like an extra attribute that stores the daily sum of sales for the store. And in that case, I don't have to calculate the sum at runtime. I can just query that result directly. So the idea here is I can reduce the amount of work that the database needs to do by just performing the mathematical task once and then querying that result directly when I write my SQL select statements, rather than having to do that mathematical task over and over and over and over again. So let's see some examples of each of these three strategies here. Now, if you recall from last time, we were looking at this fully normalized design where we had taken this big list of data, in this case, what we're calling a customer table, but we see that it has some dependency relationships in it that indicate to us that it's not fully normalized. So for example, accountant name and accountant phone depend on accountant ID rather than on the primary key of the table, which is customer ID. Similarly, the city and the state depend on the postal code, the zip code, rather than depending on the customer ID. So we know that this is not a normalized design. And we broke it apart into a 3-table solution like we see here, fully normalized design, in which an accountant table holds information about accountants, a zip code table holds information about zip codes, and the customer table holds information about customers. So we have this 3-table fully normalized design. Now, if we imagine that we want to do something like quickly find a customer's address, one of the things that we could do is we could merge our zip code table and our customer table together so that it's just one table. And that's what's shown here. Instead of a 3-table solution, we have a 2-table solution. And we've taken that information out of the zip code table and we've just parked it in the customer table. So now if we want to get a customer's address, we only need to look in one place. And that's a very desirable thing to do from a performance perspective, right? I can just look in this one single table and get the customer's complete address information. To whereas with our fully normalized design, like we saw here, if I wanted to get the customer's address information, I would need to look in 2 tables and do a join to do so, right? So in this case, if I wanted to get the customer's address information, I would get part of it from the customer table and part of it from the zip code table. And there would be a connection between them, like our foreign key here. Sorry, the arrow. Our foreign key here points to our primary key here. And if I want the customer's complete address, I have to follow that relationship, look over here in the zip code table, find the matching zip code for whatever customer I'm interested in, and then I can get that customer's city and state. And so that obviously is more work, right? It requires the database to engage in more work. So just imagine yourself as the database and you're trying to solve this problem. And I say, hey, database, give me the address for customer number 7. And so I say, all right, well, I'm going to start looking through the customer table until I find customer number 7. I say, great, I found customer number 7. So let's get their name. And here's their street address. But then I have to got their zip code, but I have to follow that relationship up here. I have to scan through the zip code table until I find the corresponding zip code. And once I find that, I get the city and state. So that's a lot of work. Now let's contrast that with this denormalized solution that we see here, where we have merged our zip code table into our customer table. And again, we imagine that we are the database and we say, how would I solve this problem? So again, our question to the database is, hey, database, give me the complete address information for customer number 7. And I say, I'm going to start looking through the customer table, and I eventually find customer number 7. And as soon as I have that row of data, I immediately have the customer's name, street address, city, state, and postal code or zip code, right? So I just have to look in that one place. There's no join, there's no second scan or lookup in the zip code table, etc. So you can see that computationally, this is faster and will yield higher performance. That is, we'll be able to answer our query more quickly. But this introduces some problems, more risk. And the risk here that we're introducing by doing this is we will be storing many, many, many copies of the city and state values for the city and state attributes. Okay? So this can lead to contamination of our database. Obviously, it's going to require more storage space. Right? So let's say that I have 1 million customers and I don't know, maybe 100,000 of them live in Los Angeles. So with this kind of design, I have to store the text for Los Angeles and the text for California 100,000 times in my database. Right? So it's going to take up extra storage space because in this example, I'm storing the words California 100,000 times and the words Los Angeles 100,000 times. Whereas with this previous design, I only need to store it once, right? Because there would only be one single row here in the zip code table, or at least a small number of rows for Los Angeles, California. So it takes much less storage space with a normalized design. All right. So with that in mind, we also need to learn how, in addition to requiring extra storage space, because we have all this duplicate data, we're now exposing ourselves to additional risk. So let's say, for example, that we have a web application or a mobile application and we ask customers to enter their information, like type in your information. So part of that is they're going to provide their address, which includes the city and the state. Now, if I have no other controls in place, I might get variations in spelling for what is truly in reality the same city or state. So one customer, when providing their address, might type in something like Los Angeles, right? Another one might type in something like LA. Another one might type in something like L period A period, right? Another one might type in something like Los Angeles, but it's all lowercase, right? So in reality, what we have is one city in this example, but because we allowed our customers to type this in and we have no other controls in place, we have multiple spellings, multiple variations, multiple labels for the same underlying concept, right? So there's inconsistency. Now, remember, one of the great advantages of relational databases is they provide a basis for doing analytics. And if I wanted to generate some kind of report with this kind of design, and I said, all right, so give me a, I don't know, like a list of all of the cities in which my customers live. Well, obviously, I'm going to get inaccurate data, right? Because each of these will be treated as a separate city, right? The computer is not smart enough to know that these all refer to the same city. Right? So I can have this bad data sort of creep into my database design when we do denormalization. And the same thing applies to states in this particular example, right? Because somebody out there in the world might type for the state CA, someone else might type California, right? Someone else might type California, all lowercase, California. Someone else might type California, all uppercase. So we can have the same problem with the state. And you can see how this introduces bad data into the database, right? I can no longer do something simple. Tell me how many customers I have that live in California, right? Because in order for the database to answer that question, I would need to specify all of the different variations in spelling and capitalization for California in order to get a correct answer. So what I'm trying to draw to your attention here is the fact that when we do denormalization, we are exposing ourselves to risk that wasn't there in the fully normalized design. And typically, we will need to do something to mitigate that risk. And that thing that we do is we need to develop and enforce some kind of new business rule. Right? So we need, in this example of asking customers to input their information, we would need to have some mechanism in place for ensuring that we don't get any bad data in these city and state attributes. So we would need to figure something out like that. And I'm sure each of you could come up with at least a few solutions to that. We would just need to design some kind of business rule that would prevent any sort of inconsistent values, inconsistent spellings or capitalizations from creeping into these two attributes after we've done the denormalization process. So one thing, for example, that you probably have seen is a lot of the websites and apps will connect to like the United States Postal Service API and will pull up the Postal Service's official version of an address, right? So you've probably seen that, or you go out, you type in your address and it'll say, hey, here is the best match to the address that you provided. So it pulls that and we can then have consistent input as long as we rely solely on those official addresses from the US Postal Service. That's one way to do it. Another way would be to write some code that would, I don't know, maybe we set some constraints, like a check constraint for the acceptable values for states. We just list the 50 states in the United States, and those are the only acceptable values. And If a customer enters anything except those, we generate an error and say, hey, you need to enter one of these 50 values. Another option would be to use some kind of drop-down box on an app, like a web app or a mobile app, right? Where we only allow the customer to select from a fixed number of values and store that in the database. So there are lots of things that we could do, but the point is that we have to do something. And that something is, it's motivated by this denormalization, right? We would not have to do it in the case where we have a fully normalized design. So if I, for example, have this design here, I can just pre-populate my zip code table with all of the zip codes in the United States and their associated cities and states, right? I would have one record per zip code, and it's a complete set. So I never have to worry about bad data creeping into this table because it's done in advance before we even ask the customer to provide us with their address. And with a fully normalized design like this, maybe some of you have seen this in your adventures out there on the old interwebs, but you're asked as a user to enter your information, say your address information, and you go out and start doing that. And all it asks for is your postal code, your zip code. So instead of asking you to type in your city and state, it just says, give me your zip code. And that's because of this relationship here. If I know the zip code, I also know the city and state. So if I have a design like this and I ask somebody to type in their zip code, I can easily and automatically fill in the city and state values on the screen that they're seeing. Okay? But can't do that with this kind of design. So this would definitely improve speed because we no longer have to do the join over to the zip code table. But we have these additional issues that we have created by doing so. The risk of bad data creeping into the database and the additional business rules that we would need to create and enforce in order to ensure that those bad data don't creep in. Now, remember, this, what we've been discussing for these past several minutes, is just one of these three different tools that we have in our denormalization toolbox. Okay. So you can merge two or more tables together. That's what we just did. We merged that zip code table into the customer table. But we have other things that we can do as well. We can add additional attributes to existing tables that will allow us to avoid a join operation, or that will allow us to avoid having to perform some kind of mathematical task at runtime, like a sum or a count or an average or a minimum or a maximum. Don't need to do that if we have some extra attribute that stores the pre-computed answer to that mathematical task.